it's past 10 minutes that we anyway have to wait. So let's start with the class. I just wanted to remember a few points of yesterday. In the body energy, that is the energy to disassemble a nucleus, or the energy released assembling a nucleus. If, let's say, we take the number of protons, the atomic number, the number of neutrons that can be seen as the mass, atomic mass, less the atomic number, we put together, packed to be enough nearby the strong force can bind them. There is a release of energy, and this energy is the binding energy. Usually it's used as the binding energy divided the atomic mass, and this is because we show clearly this increase up to iron and then a decrease after. It is peculiar. This also show us that since the relation among the Q value, the energy released in a reaction, and the binding energy, if you consider a fusion, we are fused together two nuclei of the same kind. We'll have a release in energy, and this energy release per binding or number of nucleons, it's equal to the difference of the binding energy per nucleus, actually also without the, since with the energy, binding energy per nucleus of the product minus the binding energy per nucleus of the reacting particle. So you can see that up to the iron, generally, we can have a fusion with the production of energy and release so an isothermal reaction. After, there are only fusion with absorbing energy, so an endothermic reaction. I say generally because we'll see that actually the fusion of helium, of two helium, is endothermic, is not isothermic. There is here a little fluctuation because there is not a clear continuous function. The value of the binding energy by number of nucleons, as I showed yesterday, can be approximated with the semi-empirical equation. That is, so there is a limit of the value with correction for the surface tension, and mainly what we are more interested in the Colombian repulsion. That is obviously it's this difference decrease with the increase of the number of nucleus, that as you can see here, This is also because the more nucleons we have, the more nuclei are not only on the surface. The first one are mainly on the surface of the sphere of the nucleus. So there are less bonding among them. Later, the inside is always well more populated, so it's more decrease the effect of the tension. On the other, the repulsion seems to be similar, even decrease more rapidly with the number of nucleons. But you have to remember that just after few atomic number, Z, atomic number, it's more or less half of the number of nucleons. So,
Professor,
yeah,
I forgot what was this curve here. Let me show you.
this is an empiric form.
No, this one here. No, what was this one?
This one. This one was showing that it's the behavior of 1 over x, so the inverse of the number of nucleons. This is showing that it's not that it's from a certain point, like here, it's start to be constant or more or less constant, the decrease, but still the bind energy increase constantly with the number of nucleons. Always is increasing, but increase less than number of nucleons, so I have this decrease here. This was just to show because the binding energy is strictly increasing. Is monotonic, not stop increase. It's just that increase less than a constant multiplied by the number of nucleons. So I've from this point started to decrease when we divide the energy by the number of nucleons. Just a comparison, because decrease, but decrease actually not so much. Here at the end arrived at 7.6, so it's small decrease from the top. The maximum is more or less 8.5. Here it's 0, obviously, because the nuclei of hydrogen 1 is just a proton, so you don't have to do nothing to assemble. To disassemble a nuclei of this kind, you have not put any energy, and you have no production energy when you have just one proton. Increase up to 8 and 9, then decrease by more or less than 1/4. So the decrease is really not so big, definitely less than decrease if it was constant, or increase not so much. The increase they are, but it's less than.
Thanks.
It's not increase as the number, otherwise will be constant. Decrease a little less, but is not purely a constant divided by the number. This for this reason, because sometimes it can be some. I was looking for, because usually you always find this value, the binding energy divided by number of nucleons. It's difficult to find only the binding energy, and to check, I managed to find it, to see several, and steady increase. But it's the decrease a little, because increase less than a constant by the number of the nucleus. Here, as I said, this decrease is not that they are decreasing with the number of nuclei, but actually increase, since this is, you can change with A, more or less, in alpha, number of nuclei divided by 2. So you have in power of 1/3, 6/3 divided by 4, so it's increased like the number of nuclei at the 2/3. So increase slowly, and in fact you see that here you have a different from a constant up there, small quantity, but it's also small. Then this one is, let's say that this for parity, this is because if the number of neutrons and number of protons are not equal, there are some effect, but that's important. The main part is just to remember the binding is in on the up in the left part and the lower number below iron section. You have this increase because of the tension on the surface tension effect. And then you have the function from the Colombian, because the more the protons, the more it's easily to disrupt the nucleus. In fact, here you can see that to have energy of the product less of the reacting to have positive, you have to go in this side. You have to fission, more fusion. Okay. Okay. Back again to the nuclear reaction rate. As I said, we are putting ourselves in the system barycenter with reduced mass. Remember, more or less, the as you can see in the sheet with the sheet with the constant, the Boltzmann constant is more or less approximately 10 to the minus 4. So with this temperature, you have more or less 1 kiloelectron volt. That is really low, considering what you can have in the laboratory, but this is thermical movement. The gas is local thermodynamic equilibrium, so all in experiment the particles are not in thermodynamic equilibrium, so for this reason they can be faster than the temperature. And as always, the rate is, as we saw, the velocity for the crossing section, the numerical density of the of one particle, differential of the other particle. Here is integrated minus among minus a plus that can be make no sense for a numerical density, but this is because it's integrated along the velocity. Because the numerical density depends on the velocity, and the velocity gives you the numerical density. Because just remember this one. Okay, this is n small because the numerical density usually it's small letter. In it's as for the Maxwell-Boltzmann statistic, it depends on the velocity because it depends on the energy. So we this integral at this minus infinite here just for this reason. Remember that is integrated not on the number but on the velocity. isotropic distribution, so we have the famous for P, it's uniform, and at the end you have this value that essentially integrating a mean value, like we remember in the maximum statistic. To have a mean value, you integrate the value that of the characteristic you want, the property, among multiplied by the distribution on the all the value. Here it's 0 infinite because it's the module, since it's a tropic, so it's equal in all the direction. You just can just consider the module of the velocity, not also the direction. So at the end, the rate is the multiplication among the numerical density of the two particles by this value that is the mean of the product among the cross section and the velocity. That are the two three main characteristics of the Fourier reaction. It's how many particles you have. The more the dense, the more you have interaction reaction. The higher the velocity, it's easier to have more interaction, because you have for each second you have unit of time, you have more particles that are passing nearby the target particle, and the cross section that indicates the probability of interaction. Originally, as I said, was the geometric size of the particle. You have a target, a bullseye. The bigger, the easier to hit it. The smaller, it's less easy to hit it. This is work in classical situation, in particle situation, quantistic situation. You cannot talk more about size of the particle, because you cannot measure the size of particle. Anyway, you can have, for example, to throw something to the particle, but this is giving you the cross section, not the size, the actual size. So sigma now is essentially the probability of interaction, of collision among target and projectile particle. If the number is the particle are the same, you have to divide it by 2, because you have to consider a pair of particles that is possible. While if it's different, the pair is just how many in one kind from the number of the other. If they're the same, obviously a particle cannot be paired with itself. So it's you're losing half of interchange. Also, one couple is counted twice. Actually, you can, as we saw previously, simply put divided 1 plus the delta. Two particles, the delta is said is 0. If they're different, one if they're the same. In this automatically the formula correct for this case. The mean life of one particle can be simply calculated by the numerical density of that particle divided the rate. That remember is the density rate actually, because in gamma interaction for unit of volume, for unit of time. And if they're the same, they're not alpha. It's just divided by, it's like here. At this point, we have what we are most interested in. These are exactly are given the number interaction for volume for unit of time. So if I multiply by the Q value, that is the energy released by each reaction, the the power of the nuclear power release, but in this case from this particular reaction, it's just a rate multiplied the Q value divided the density, since this is a density of number, numerical density by time, a rate. This energy, this will be energy by volume, dividing by density, you have the energy by mass. Changing, we can write in this way, with our just density above, and this value, the fraction motion from one particle, the fraction for the other, divided their number of mass. Yeah, number of mass, not number atomic mass. Atomic mass is the mass of the atom, so it is different. The atom in the mass number is the number of nucleons inside. That this is exactly the inverse of the atomic mass is defined molecular mass we saw before, so you can rewrite this one, put the one divided mu A and the one divided mu X. I corrected the notes and send the new version later. This is okay. This is the value for the energy that we are interested. Using when you see later, knowing the several value, we can put have a value for our power, nuclear power, and put it, as I said before, we comparing with the mean that is chosen by cyclone by grams. You can see how many, what is the fraction of mass that is where there is an actual the nuclear reaction. Comparing this exact value with the mean value calculated on all the stellar mass. Now let's see one problem, because what we are interested, this is known, this is known, the more or less is known, defined by the distribution. We need to the sigma, the cross section, that is the probability of interaction and the reaction. Because something is that they are interacting, colliding, and something that we can have a reaction, actual and interaction of the nuclear reaction. If you're going to see in the classical, we have potential well with the Colombian barrier, and a projectile that arise. The Colombian barrier rise and then goes down. There is this hole here, and here is the potential. That is the centrifugal part of the particle and the Coulomb. The problem is that when you are considering the energy, the minimal distance at which a projectile particle can arrive nearby the center is just defined by the potential at that position that has to be equal to the kinetic energy infinite far away of the particle, where this potential is almost zero. And as we know, a particle has a temperature in a stellar center of the sun. We can calculate, as we saw with the static equation, that here the central energy is more or less 10 to the 7 Kelvin, as we saw before the energy, so it's 10 to the 7 multiplied by 10 to the minus 4, 10 to the 3, so is a kiloelectron volt. But if you check, usually the barrier of Colombian barrier at the top of the border of the nuclei, they can then start the strong nuclear force, and it's definitely in the short distance stronger in the attraction of the electromagnetic force, so you have this potential well, but this top is of the order of mega electron volt. This means that when there are several thousand times the typical energy of the principal, the peak of the velocity distribution. It means that only the far tail of the maximum distribution can have enough energetic particle to pass the barrier. It is not enough to have this kind of luminosity for the sun with that mass, so that eternal temperature. So actually, for the classical, it's impossible. Another point, actually, since the thoughts are almost conservative, if you have a particle that are in age to enter here, has also enough energy to go outside, because it's symmetrical. It's just one side, but you have to think like a pole, like for the skateboard. You can see, if you are on the top, you are going side, you exit. And so the other, so technically also a particle here should not manage, because it's really difficult that manage to get trapped by nuclear force. They are really strong, but is trapped, then have enough energy to go outside. In fact, approximately 1 century ago was discharged the idea of nuclear fusion, because it was impossible. The idea, one of the first idea was that the sun was burning coal, really, and they thought that the sunspot, the solar stellar spot, you can see this black spot was actually coal that you can see. Then they realized that are actually black, or less dark spot, because they are at just 4,000 Kelvin, not more, little less than 6,000 on the surface. So they are emitting definitely less, so they seem dark. Was thought about gravitation, but then Kelvin Helmholtz with the calculation showed that it was not possible. As soon the geology showed that the Earth was really cold, so it was not possible that because there are just several hundreds of millions of years to produce energy in contraction. And the fission, I don't remember, just this one was not, the fusion was rejected because it was totally impossible. Then the quantics start to be studied, and in quantics there are the potential well at the peculiar behavior that the particle have in the potential well, that are assumed here because are important in general. In at the beginning, essentially also, if you have a potential well and it is below the zero, as here, and a particle with positive energy. So its energy is always positive respect to the basic. So classically, as said before, like in a well for the skateboard, the circuit, you arrived with the energy, enter have more energy, and then you have enough energy and you go down. So classically, the transmission is one perfect because there is no reason why you cannot pass this potential wells. But in quantics, if you do a calculation, you can see that the actual transmission is something like this, and so on. So it's beginning at 0, then with increasing the energy, it's start to it's 1 some point, but not always. Mainly, it's not perfectly 1. That means that a particle that arrives has not 0 probability to be scattered away or to enter and be trapped a little inside, because the transmittivity is equal for the two barriers. And then the probability then go through, be scattered inside, or be trapped a little. So actually, you see, for quantistic, it's only possible that particle can, in potential or potential well of this higher energy, can be trapped inside. But the most interesting part here is that we consider a potential well actually a barrier, and a particle colliding with this potential barrier. Usually, you have that the particle stop to exist at the barrier. Classically, in a box, classical, the particle just bounce here from the two walls, simply. And there is no probability to find the particle outside, inside the wall, you see. Instead, in the quantics, the particle have a probability to go through the barrier. This probability of the transmission, its proportion, it's decreased with exponential of the size. So the biggest is this wall, this barrier. The smaller is the transmission, so the probability to find outside. And going in here is that with a potential barrier in Coulomb with a nuclei, in the particle arrives and has this tunnel effect that the particle has always a decrease in probability. Here is not connected to the energy level. I just start at the same point because it was easier to show. It's showing the probability of the particle to enter. The biggest the barrier, the less probability have at the end to enter. But can have always, because it's an exponential, so you never got to 0, a probability to enter inside the nucleus with the certain energy that is given from the total energy here. So enter with higher energy, and say before, for the same characteristic of the quantics, the particle stay trapped a while inside. Obviously, depends on the energy, so it's not trapped forever. For this reason, the cross-section for the nuclear reaction, it's a little more complicated than the classical one, and it's combined by several parts. The cross-section will be explained this way. this part. This is the geometric cross-section. 2L plus 1, that are the quantity number for molar angular momentum. That it's essentially, this part is connected with the geometric meaning of the particle. In fact, this is a lambda divided to pi is the wave number. Maybe you should mention at least that is connected with is energy, that is essentially the size of his wavelength of the particle. So something that is called the size and quotation mark of the nuclear particle. It's not the physical size, but the size for this function. So is the actual size, where because two particles that are near this size cannot be distinguished. The two wave function are too near, corrected as said by the quantity number of angular momentum that is connected with the impact parameter that classically will be the distance from the minimum distance among the direction of the projected particle with the target, the minimum distance that the two particles can be classically. This is a little different. Here you can calculate so the angular momentum of the projected particle respect to the target. So it's a quantum, and to check that that the value has to be smaller the radius of the nuclei, the radius of the nucleus, because if it's bigger, obviously they are missing. You see that L have to be 0. So okay, is there? I mentioned, but you can forget because the 0, so it's just 1. In the other value, it's this omega. This is just a statistic factor for the spin and internal angular momentum, depending on this kind. You can have a correction when angular momentum on the interacting particle, and considering also the compound nucleus created by reaction. Then there is what we are most interested, that are transmission for A, that are the part that consider now also the tunneling effect. That is normally this value with gamma, that is the width of the channel, that is essentially the inverse of the mean life of the channel inside of the nuclei. No, after because we see a little later. D is the size of the energetic dimension of the state that we created. Then there is a resonance factor that we'll see later that has the shape, and just as previously you can see that to have this part bigger, that is what we prefer, because the biggest is each of this part, the biggest is the cross section, so if we have more reaction. To big this one, you have to be smaller than the denominator, and since it's the sum of two square, you have to minimize the square. This is just a constant because it's the width of the channel. Here we have the difference. So when the difference is 0, this is minimum, so this is maximum. Then so you can see that this equation will be at a maximum of the certain value of the energy. Then there is a symmetry factor, symmetry for nuclear physics meaning. Then what is the branching ratio? It's G, that just the probability of the channel that we are interested in outside. So obviously the cross section of the reaction is depending on the reacting particle and on the type of reaction you want, because you can have for several so here in a reaction, in interaction, we create a compound nuclide, but we have several channels how they can exit the reaction, because the elastic scatter, in elastic scatter, they are not extending. In our case, it's not the nuclear reaction we want. We can have the reaction that we are considering. If we are just unify the particle and exit a subparticle, if you have a fusion or a fission. Fusion in this case relatively capture, simply because if you have the fusion, we're just releasing the not the binding energy, but the difference. And the Q value, that is the energy to bind the new particle inside. Okay. Then, if you consider all this part put together, do all the calculation, we get these awful things that is mainly constant. And inside here we have an exponential that are the part, this exponential that is due to the Maxwell-Boltzmann, and this part that it is in the transmission of the tunnel. Obviously depend on the potential, because as I said, the transmission depends on the size of the potential, so depend on the characteristic, so the atomic number of the two particles, the charge, the reduced mass, and the energy of the particle, obviously. And you can see that the particle enter in minus 1, the square root of the energy, because square root of energy is proportional to the velocity. And we have an interaction with the velocity. If you look at this, and we plot, you can see here, spotlight, the famous graph with the Maxwell-Boltzmann curve, then transmission that they are cleansing, and this should be, I think, not exactly linear, but you can see with usually in should be really difficult. Anyway, it's quite difficult. The product of these two created this bell shape of the increase, because here there is really low, where are more particles, approximately with the temperature typical of internal energy of the link sequence is 1-3 kiloelectron volt, mainly in the particle. The transmission is really low, it's too small, then it's but here where transmission is higher, you have a small amount of particles. So the production of the two create this bell shape. In fact, is usually also approximated with the Gaussian for the calculation. And this is what is called the famous Gamow window. Gamow was the one that discovered that tunnel effect. So permit to show that yes, stars can use fusion, and you have this, luckily, this small size. You can see that the size is just few kiloelectron volt, not so much, and in a region also with not so much particle actually. But as we saw later, sometimes it's not the number available, it's the probability to have something is just the rate global, that is the density, the actual number of particles you have multiplied for the cross section. So you have a small probability, but definitely enough particle to have it. One example is, for example, the fusion of two protons to have the deuterium, that is the beginning for the proton-proton, is definitely not really probable reaction. It's mean life, the production is like, if I remember, 10 to the 10 years. So every 10 to the 10 years, a particle manage to have one reaction. That since the sun has few 10 to the 9 years, that means that there are particles that up to now didn't manage, obviously, to interact, because you need an age of relief. But the reason why the sun is producing so much energy is because you have a lot of particles. Just in 1 gram of hydrogen, you have 10 to the 33 particles. So even in 1 year, you have 10 to the 13 reaction. So you can understand that you have enough particle to have enough reaction for to produce the energy you need. Why is mouse? Okay. This one in spotlight. And we have a maximum of the energy for the maximum of the center of the gamma of the windows, that is this value that you can see, depending on the typical energy, can vary from 5 to 100 kiloelectron volt. They are not so much, you can understand, but at least it's permitted to have an reaction that bring that at the end, if you do all the calculation, you have the mean value from the cross section multiplied by velocity. It's this value that depend on the atomic number of the particle, the temperature, and here is A is the reduced mass number of the two particles. As we can see, definitely if you increase Z, we'll have difficult. At higher Z, we have need greater and greater temperature to have the same reaction, to have the same quantity of this value. So with the same energy production. Usually, since the two particles are equal, you can put together, and here is this Z is Z to the fourth. A is more or less like proportional to Z. So it's the atomic number, the mass number to the fifth power is a lot. So if this hydrogen, it is 1, but if you go for the helium, it is 2 to the fifth power is 32. Is definitely higher. It's not in this actually, in fact, you need to arrive 10 times more the energy. And at the time the temperature, you need usually 6 million if for the hydrogen. For the helium, you need to arrive 100 millions of Kelvin. Another thing is that when increase the atomic number, the potential increase. Yeah, so it's the potential is more difficult to pass through, but also the velocity of the particle decrease, because the velocity is the quantity divided by the mass, or if we connect with the energy divided by the mass, and is the energy that is distributed equally among the particles by Maxwell-Boltzmann distribution. So the ions, the heavier they are, the slower they are. So you have, as we saw, it depends on both sides. The probability depends on the energy of the particle that is connected with this, also with this velocity, with the energy, and the other. So it starts to have a lower velocity, and you have less interaction, because to interact with the nuclei, you can have more or less the same energy actually, but for the rate, that is the cross-section multiplied by velocity, you have less particles that are passing by for each second, and this goes down. Okay. No. I change a little. Now it's time to see the resonance, as we talked before in inside the cross section. This section is there is also the part that is connected with the resonance. Why this? Because we realized that actually there are some reactions that happen really more than the others. There should be so much reaction according to the calculation, and then we see that actually it's not we have more reaction what it should be, and this why. The reason is because the a nucleus can be quite similar also to the atom. You can have equally a shell model for the nucleus inside of the nucleus. Like for the atom with the electron, you have the electron outside with orbital of several energy. So the atom can be at several energy, the lowest with all the level field and the electron is the lowest state energy state possible. Then excited level with the electron, they are in other orbitals, energetic state higher, something like that. Similar is the okay. In the wrong position. Is similar here. Then you have the potential, and inside you have the minimum, the bottom. Then you have the several bound energy of the atom inside below zero, where they are stable level, where you have the several nucleus. And the nucleus, like before, is a little different because we just electrons, so 2 electrons because of the exclusion boundary principle. Here we have not just electron, we have proton and neutrons. So in each energetic state, we can have 2 pairs, 2 proton and 2 neutrons. But you can have several. There are when you have the interaction and create the compound atom nucleus, the projectile particle A have an higher kinetic energy because the sum of his energy outside plus the bound energy here. So it's respect to the bottom, it's higher. So you consider the bottom of the potential well. And in some case, this energy can be exactly, because if it's around here, it's a stationary level is stable, no problem. But if here, you can have the particle is in stable place, so exit out, you have scattered, or in some part you have a quasi-stationary state. That means that have with in a lifetime that is a little longer what it should be. That means the particle start to bounce internally. There's a little this wave function managed to stay trapped inside, and a little longer to permit to redistribute its energy among all the other. Once the energy is redistributed and not enough energy, the single particle to escape easily because each particle is found lower. This cause the energy profile on this side, they enter in the cross section, and we saw at this peak. So it creates that little higher situation. Here is just a correction, should be here 1 multiply, but we have this one. And let's see. And thank you. This one. As here you can see, we are deriving particle nuclei at the tunnel, and here you can have some bounding energy inside that are excited, yes, but you can have some more stable situation, like you can have some atom with electron that are in excitedly and far away, sometimes with more energy than the ionization, but it's possible. And similar here. And this cause that you have the classical Maxwellian, that the tunneling effect, the gamma, and you have multiplied by the resonance. That is far away, increase not so much, but if it's enough nearby, the energy of the maximum of the gamma window, and the resonant energy enough nearby, you can have a definitely increase in the rate in the cross section, so in the rate on the nuclear reaction. And you will see there are several important reactions that have resonance, and that's permit to have more reaction that it should be. If I remember well, it's exactly the helium. That is, to burn helium, you have to do 2 reactions in short time. The second is a resonance, and this permits to have a really good result in burn helium burn. Another point is the electron shielding. It's I mentioned before, for the plasma, they have the nuclear, the Colombian is what is the particle is not more interacting with the Colombian interaction with the single particle with the in general, because the particles saw the plasma as something more uniform. This is something connected. With if you have high density, obviously you have a lot of electrons, because all the ions, all the atoms are ionized, so they are producing. Hydrogen produces just 1 electron, but helium produces 2, and so on. So you have a really good number. If you have in this way this bath of electrons, a lot of electrons inside the nucleus. Nucleus ionized, so ions, so they are positive charge, the electron negative charge, they attract each other. What you get is that in the nearby of the ions, you have a higher probability to find an electron. But if you have a lot of electrons, that means that another particle that arrive nearby see the global potential of the ion plus the electron. So the potential is lower. So the Coulombian barrier it's lower. So you see, the nearby we have the density, numerical density of electron is higher than the mean, and this go with this equation that is go with the exponential, where phi is the electric potential equal the charge, and usually this potential is quite smaller the thermal energy, so you can approximate this way to the calculation, and we can see that for radius higher than the baby radius, as mentioned, characteristic for plasma, the potential have this size. So have the classical Z multiplied by the charge divided by the distance, but it is an effect of reduction. The further the smallest is the potential, so the particle manage to arrive nearby. And classical value for temperature of 10 million Kelvin, density among 100 grams per centimeter to minus 3. That is more or less typical density inside the star, the 3 also. You have that the radius is quite small, 10 to the minus 8, 10 to the minus 9 centimeters. You do the calculation, you see the electron shielding can be approximated with the formula that is proportional to the density and inversely to the power of the temperature. And also here, this is the confrontation between the size and the size of the atom. It's bigger, and so far away, more nearby, obviously, it's the potential is the same. This one is important. When the higher is the density, the more important is the electron shielding, obviously. At some point is the density is so high that you start to have picno-nuclear reaction, no more thermonuclear reaction. Picno is density. So it's a reaction, nuclear reaction, that are depending on the density, not on the temperature of the gas. Thermonuclear is so called because the rate depends mainly on the temperature of the gas, because the velocity, how the particle manages to interact is due to the thermal energy. When you have a picno-nuclear, it's just because the particles are so well packed together. At the end, we can okay. I remember that I did some change. Didn't remember. Here, no, okay. Okay, here I remember to put here exactly uncertainty in principle or Heisenberg, energy, temperature are energy and time are conjugate variables, so the product of their uncertainties must be equal or greater than the Planck constant, reduced Planck constant. That means the half-life, the life of a state is inverse of its energy.
¿Cómo la accionó cuando se pone?
Marcelo,
Ahí me gusta pura tonteras de TikTok. Hola.
you want to ask something?
Marcelo, muteate.
Hmm?
Ahora sí, profe. Siga.
Ah, okay. Okay, to finish. We can see at the end in the production, nuclear production, energy produced by unit of mass, unit of time. It's this value. We introduce all the term. This is just constant because it's these are the atomic mass, molecular mass of the two particles. Q is fixed for the reaction. This is just a constant. The density is this one, and we can put like a constant for a zero value of this mean, correcting, and usually depend for the with the density and the temperature in the two exponent. Usually the density is just one. The nuclear the energy production goes linearly with the density, while for the temperature can have several values, even really higher. At some point you can have the exponent that goes to 20. That you can see that a small increase of temperature is an enormous amount of energy production. For the but here we could depict a little more. The typical nuclear reaction, usually the density for to burn hydrogen is 10 to the 6 gram. To burn the helium is 10 to the 9, and the carbon 10 to the 10. This is the typical. You can see there are definitely high value for the density to start nuclear reaction do simply for increase of density. They are packed together, so the particles start to get a fusion because they are too close, really near among them. About the cross section, usually you have zone that can have this really big value. It's complicated. The easiest way to usually to calculate everything, the cross section is just written as a S section, a function that is not depend a lot from the energy divided by energy, and multiply for the exponential part. This permit to do instead of usually of calculate everything, you can Yeah, you can calculate just in a way that the cross section in laboratory, and then try to derivate the value for a specific case, in a stellar case. And in fact, then here you can see this is, for example, this is an example. This is a graph for experimental with several values calculated for the cross section. Here, I don't remember which one. Ah, okay, it's from the, I think for the deuterium with the proton. You extrapolate and then you see. And here is a mega electron volt. We are talking about, we are in nuclear situation in kilo electron volt, so we are here. You have this one, you calculate your value, and then because the exponential part is well known, the part depending on the energy of the other, okay. All the part before can have several not easy part to calculate for the to the characteristic of the nuclear reaction, and so you calculate in this way. The problem is when this here in the nearby there is a resonance that is something more that adds, so the total rate of the reaction is not more easily calculated in this way. As I said, is not that it's calculated the nuclear cross section perfectly from the scratch. In some cases you can, other it's complicated. What you do is use result from laboratory that usually have higher energy, but you can derive below and see what should be the value and put there. And yep, this one. You can see here that for several, for example, this is the CS0 for the value in general, and then you can see the first derivative, expected energy. Here is the unit of value, B for barn, that are the a unit of measure for the cross section. It barn like the building for the hay, because the first use for the uranium, in fact, the uranium has essentially one cross section with the cross-section reaction of the uranium with the proton is 1 barn, that is 10 to the minus 24 centimeters square, really small. And it's just because they do the joke, this saying that the nucleus of the uranium, it was big as a bar, or easy to eat, but okay. But you see here the first derivative, so how S depends on the energy, it's really small. So the assumption is correct, and you can assume that approximation. With this part, we start to do tomorrow with the actual nuclear reaction. They are inside the stars, in start to understand how bad the things can go in some situation. Any question? I think maybe you are, because
Tengo una pregunta, profe,
mm,
pero es como en general. Esto no lo pude encontrar en el DINA.
this part is not really well in the Dina. Dina es muy rápida en esta parte. Lo pone un poco más en el otro libro, quello que tenía Gasimov. En esta parte generalmente es un poco más superficial. Escribe menos que el Dina, pero esto mejor manteniendo en Dina. El otro hace más un resumen. En esta parte pone un poco más detalles. Sin embargo, Dios, si quiere más detalle y Kitteman me da. Pero para curiosidad, porque, diciamo, la cosa importante, yo he visto de dar un poco de detalle un poco más, porque, diciamo, puede ser también interesante comprender algunas cosas más que hay. No las fórmulas. Estas fórmulas nunca va a estar. El electron shielding es comprender qué pasa, más que recordarse un montón de fórmulas. Porque no es un curso de física nuclear. Es un curso de astrofísica, estructura y evolución estelar. No tomamos todas las ramas de física y la usamos. Solo que para usarla es necesario que ustedes yo esté seguro que ustedes se la saben. Entonces, le he mencionado la varias partes de manera de estar seguro que el concepto, se no lo habían ya visto, menos una base lo tenga, como la boca de potencial, la mostrada, las características. No me pongo a hacer los cálculos, es absurdo pedirlo, porque no es parte del curso. Se tiene un montón de otras cosas, que son las implicaciones astrofísica de lo que pasa. Por ejemplo, esto poco, porque esto era justo curiosidad, la parte, no sé, que la cross-section es definida en esta manera, era solo para mostrarle anche, después se le paso anche el artículo, que tiene varias cosas interesantes, ma no hay approfondimento. Quello che è más esta parte, que come varía con densidad de temperatura. Esto porque para cada reacción debemos ver cómo son estos coeficientes, los exponentes, y sus valores son importantes. No siempre recordarse los valores exactos, pero vamos a ver que hay un fuerte cambio entre una reacción y la otra. Y como decía, hay alguno que va a 40, uno de estos es el helium burning. El helium burning tiene una tremenda dependencia con la temperatura. Iremos a ver que lamentablemente varias estrellas, precisamente estrellas tipo come más o menos un poco más grande que el Sol para abajo, hacen el helium burning después de haber degenerado. Cuando la temperatura no comanda más la presión. De consecuencia, vamos a ver que esta cosa son efecto bomba. Dependiendo un poco de la situación, va a hacer que la bomba se hace realidad, destruye la estrella o simplemente bien apagada rápidamente. Esta parte, esempio, la ventana de Gamma Windows, tú tienes que saberlo, porque si no, no se explican no se explica las reacciones nucleares. El valor exacto, penso que solo un teórico se lo recuerda. Ovviamente, ricordarsi che dipende dal numero atomico. porque esto, más que todo, porque el potencial depende de esto, entonces la ventana depende de esto de seguro, porque no, no, no la veo. No la veo dibujada. Ah, no, porque la había mostrado. Ahora la he mostrado del otro lado. La, la ventana, digamos, è importante, sono dos contributos exponenciales del tunneling que me da esta ventana. Esta se tiene que saber porque eso me explica por qué tengo reacciones nucleares. Si no, no podría tener suficientes reacciones nucleares en estrellas. Esto es una cosa importante en comprender cómo funcionan las estrellas. Y esta segunda parte era para dar esta parte de la ley de conservación. Son importantes porque, como le he mostrado otra vez, yo le he descrito toda la reacción sin tampoco recordármela. No me estoy preocupando. No, la protone, que es una de las pocas reacciones que se tiene que saber a memoria. Yo no me la recuerdo a memoria, yo me recuerdo las características, qué partículas interactúan, y después todo como quello que viene después me lo voy con la conservación de la carga, del número barionico, el número leptónico. Que vabbè, quella dello spin estaría más ya se resuelve con esos dos números. De consecuencia, esto no es tanto que tiene que saberlo, aunque se necesita así, porque hay cosas que se debe conservar la energía, la carga, el número bariónico, más que todo es conveniente para ustedes, porque después se puede calcular las cosas de la forma que era una reacción fácil de escribir, porque sabes X, A, Y e Y, se sabe con qué interactúan, cuál es el producto principal, y después la cuarta se obtiene directamente en la ley de conservación. El Q-value y la binding energy se tiene que saber anche porque se no se explica cómo es que la funcionan la reacciones, cómo se produce la energía, y de hecho, la razón por que he dado esta pequeña tarea que hacer. Esta no, obviamente, esta no era la cosa de física nuclear. Podría ser algo interesante si tú quieres estudiarte física nuclear de las partículas. No, la única importancia nuestra es el máximo al hierro, quello che interessa, perché questo se va tiene risultato un effetto astrofisico nelle estrellas. Razón porque cuando llega a la producción de hierro, después la estrella muere. Porque esta forma, más o menos, ma simplemente non con los detalles della formula. La pulsión colombiana e effetto de superficie. Que, vabbè, esta parte es bastante obvia. Hay muchos protones uno al lado, entonces es más fácil que tendan a escaparse uno del otro. No son conceptos difíciles que se tienen que saber. Después, a ver, esto era clásico cálculo que se muestra para obtener il rate è parte di quello che si mostra. Ma non vuoi certo pedir il posto di potenziale, è una cosa di quantica. Ma il fatto che sia punto di potenziale, la caratteristica la necessito nel parametro di trasmissione, che non vuoi, infatti, la otra vez avevo mostrato un poco más de fórmula, esta vez completamente cambiado porque es totalmente inútil. Esto es interesante saber en general, por la cross section, cosa depende, ma ovvio dipende dal impact factor, parameter, ovvio, fatto área en donde puede interactuar, cosa de transmisión y cosa que puede interesar, porque el otro es menores, la resonancia, el branching radius, che appunto la parte che dipende dal canale, del channel. Porque a seconda de la reacción que tenemos varias probabilidades. No son todos iguales. Hay una y otra. De hecho, queremos ver. Hay reacciones que elementos que crecen de manera diferente. Sí, pero... No, me parece que en algún caso hay anche proprio prodotto differente. Mismas partículas que interactúan, pero el resultado puede ser un poco diferente porque hay branch diferente de resultado. La cross-section depende también de quello che tu quieres. Uno famoso, ad esempio, el decaimiento, hay varios decaimientos de partículas, interacciones. Se puede ver el decaimiento del protone también, pero es un canal que es muy poco probable. Una cosa que necesita 10 a la 32 años, algo así. Ecco, esta parte es pesada, es tal vez un poco aburrida, no es fenomenal, pero es una parte necesaria, porque para después es necesario comprender las cosas, porque hay ciertos efectos que resultan, son todas cosas que tienen un efecto sulla reazione nucleare che viene in estrella e estas son la vida de las estrellas. Bueno, ahora me parece que está comenzando a ser bien tarde porque se tiene otra clase, comienza.
Sí, profe.
Ok,
Ya.
nos vemos. Chao.
Nos vemos. Chao, gracias.
De nada.
Sorry.